So I wanted to finish off this section with just working through a couple examples that I think are similar to what shows up on your homework. So just wanted to look at examples 11 and 12. So, and this is in part A. So we're going to consider these following sets, and I want to draw an example of an element of these sets A, B, and C. So A here is the set of scalene triangles intersected with the set of acute triangles. So remember that this symbol, this kind of upside down U, means it's the intersection of these two sets. And so this means we want to draw a figure that is both scalene and acute. So we want a triangle that is both scalene and acute. So scalene means that none of the sides are the same length. And acute means all of the angles are less than 90 degrees in my triangle. So I want to make sure I draw something with, I want it to not end up accidentally being like isosceles. It's hard to do. It's not super obvious that I've done that. Let's see. Sorry, I'm just trying to move things around so it's not super obvious. Okay, maybe that's more obvious. Okay. Okay, so something like this. It looks to me like each of these sides have different lengths, and all of the angles are less than 90 degrees. Okay, so B wants us to intersect I and O. So that's, we want a triangle that's both isosceles and obtuse. So we want one angle in this triangle to be bigger than 90 degrees. And we want it to also be isosceles, meaning we want two of the legs to be the same length. And those two legs that are the same length are going to have to be on the sides of that obtuse angle. Otherwise, I think that's right. I don't think things will work otherwise. So here's, I think, an example. As long as I didn't accidentally make it a right triangle, which I don't think I did. Okay, so here's my angle here that is a little bit bigger than 90 degrees, and then each of these legs should be hopefully approximately the same length. Okay, we can label it this way. There we go. Maybe it would help to label that these three legs are the different lengths. Okay, and for example C, they want us to look at O intersect E. So let's see. This means we want an obtuse triangle. So again, something where one of the angles is larger than 90 degrees, that is also equilateral. So notice the directions say draw an element of this if possible. And here's one that I think is not possible. This is the empty set is one way of writing it. This is not possible. And the reason is that if we have an equilateral triangle, then all of the sides have to be the same length and all of the angles have to be the same size. And since all of the angles have to be the same size, let's say I'll label them 1, 2, and 3. So measure of angle 1 has to equal measure of angle 2, has to equal measure of angle 3. And they all have to sum to 180 degrees. That means 3 times the measure of angle 1 has to be 180 degrees. Or 3 times the measure of angle 2 has to be 180 degrees, however you want, or 3 times the measure of angle 3 has to be 180 degrees, right? So that means each one of these angles has to be 60 degrees. And so none of them can be larger than 90, okay? Great. All right, let's look at example 12. So similar concept, but this time instead of looking at triangles, we're looking at more general um, polygons. So let's consider the following sets. Okay, so here in 12, we have the first example is K intersect P, so we need something that's both a kite and a parallelogram. Okay, so remember, to be a kite, it means that the adjacent legs are the same length. And to be a parallelogram, it means that all the sides have, or all the opposite sides, pairs of sides have to be parallel. So the two pairs of opposite sides have to be parallel. So I think the only way to do that is if we create a square. Okay, so basically you can start by saying, okay, the kite says I need these two sides to be the same length, right? Because they're adjacent. But I also, the parallelogram says that I need something to be the opposite sides to be parallel. And so you can kind of see when we end up doing this, we end up forming a square. And I think there's no other option. So they don't ask us what set this is equal to, but it is equal to this set of squares, I believe. Or actually, I think rhombi. I think any rhombus will work. Sorry about that. Any rhombus should work. Doesn't have to necessarily be a square. Okay. B says, let's look at I intersect R. I is, I think, the set of isosceles trapezoids. I don't know why this one looks like an L to me, but I think that's supposed to be an I. So the set of isosceles trapezoids and the set of rectangles. So remember, trapezoids, trapezoids have exactly one pair of parallel sides, and rectangles have two pairs of parallel sides. So if there weren't this word exactly, I would say, oh, this is totally fine. We'll just draw. We can draw something like this, or at least a trapezoid that is a rectangle. But since there's this word exactly here, it means I can't have two pairs of parallel sides for a trapezoid, and so this should be the empty set. So if I can't do it for a trapezoid, then I certainly can't do it for an isosceles trapezoid. All right, now looking at C. Okay, so remember, this notation means we're going to look at the set P and take out all the elements of the set B. So the set T is the set of all trapezoids, and we're going to take out all of the rhombi. And that's weird because I don't think there are any rhombi in this set based on the previous definition. So I think as long as we draw any, oh, sorry, P. I don't know why I was thinking P is the set of parallelograms. There we go. So we're going to look at the set of parallelograms and take all of the rhombi. Now this makes a lot more sense. Okay, so it has to be a parallelogram, but it can't be a rhombus. So I think that's not too bad. Remember, rhombi have just 4 equal side lengths. And so as long as we draw a parallelogram that doesn't have 4 equal side lengths, we are fine. This is, oops, let's just redraw it. There we go. So this is the I think this should be the non-square rectangles, I think is all that would be in here. But there's at least one example. Okay, let's do 2 more examples involving angles. just for good measure. I'm so funny. Okay, so in this figure, we have a bunch of angles, and we want to determine the measures of these two angles. So what do we want? We want to find AFB. So AFB, that's just this angle, and CFD. So CFD, that's this angle. Okay. And let's see what we know. We know that the measure of angle BFC is 55 degrees. So BFC, that's this angle. Oh, and these aren't necessarily the same. So let's maybe, I'll put these in pink so that we know what we're looking for. They're not necessarily the same. They're just the two angles we're looking for. So, oops, good enough. Okay, so those are the two we're looking for. And we know that this angle is 55 degrees, BFC, and we know that AFD is 150 degrees. So that is this whole angle is 150 degrees. And the last thing we know is we know that the measure of angle BFE is equal to 120 degrees. So that's this angle is 120. Okay. So let's try to write some equations, or sorry, some equations for what we do know here to spell this out. And I'm thinking, I was thinking I might want to just label my different angles to make my notation a little bit nicer, but I probably won't actually, just because there are too many things that I would have to label if I include those bigger angles. Okay, so let's see. What do we know here? So let's start with some of the sums we do know. So let's start with kind of the most obvious one that we do know, which is that the sum of all four of these angles should be 180 degrees, right? So actually, maybe I will label these little angles in between. Let's do this. Let's call this one 1, 2, 3, and 4. So what we want is the measure of angle 2 and the measure of angle 4, okay, in this notation. So what do we know? We know the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 altogether is going to be 180 degrees. We also know that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3, so just these rightmost three angles, should sum up to 150 degrees. And let's write the last sum. We know that the measure of angles 2, 3, and 4 should sum to be 100. Oh, sorry, this one's 120. Let's write that. So the measure of angle 2, measure of angle 3, plus the measure of angle 4 should be 150. That one's 150. There we go. Okay. So now we can also, if we want to, use the fact that we already know what the measure of angle 3 is. That is just 55 degrees. Oops. So let's go ahead and substitute that in. All right, so actually I think immediately we can pretty quickly see that find the measure of angle 4. So let's look at these two equations. And I think if we just add them straight down, we should be able to get the measure of, or sorry, subtract them straight down. We should be able to get the measure of angle 4. So, so basically this top one, so here, these are the three that I started with. This top one says that the measure of angle 4 is the measure of angle 1, or sorry, is 180 minus the measure of angle 1 minus the measure of angle 2 minus 55 degrees. And this whole thing is negative 120. So that means the measure of angle 4 should be 180 minus 120, which is 60 degrees. Okay, so now we already have angle 4. We really just need angle 2. So let's see. So I think we can now, so we've used this equation, and it was what we started with, and then we plugged in this equation. So now let's go ahead and look at this third equation to tell us about the measure of angle 2. And it says that the measure of angle 2 is plus 55 degrees plus the measure of angle 4, which we know is 60 degrees, is equal to 150 degrees. So now we can just go ahead and solve for the measure of angle 2. So 55 plus 160, let's rewrite this, measure of angle 2. 55 plus 160 should be, oops, sorry, this is plus 115, I think, is equal to 150. And so the measure of angle 2 is equal to 150 minus 115. And I think that's 35 degrees. Okay, and those were the two that we were looking for, measure of angle 4 and the measure of angle 2. Great. Okay, so this was number 13. I'll finish off with this example, number 14, and talk about a couple of starred exercises. I'm going to move this work up. I think that will help. And then I should have enough room for number 14 here. Okay, let's look at number 14. So number 14 is a similar idea. In the following figure, we know that the measure of angle 1 is 9 degrees less than the measure of angle 2, and we want to determine the measure of angle 1 and angle 2. So again, we can use a similar idea where we set up a couple of equations. And it doesn't matter which one we do first, obviously, but we can use the same type of equation where we have two supplementary angles here. So we have that the measure of angle 1 plus the measure of angle 2 should be 180 degrees. And we also know from the statement that the measure of angle 1 is 9 degrees less than half the measure of angle 2. I'm sorry. So that means the measure of angle 1 is 9 degrees less than half the measure of angle 2. So half the measure of angle 2, and it's 9 degrees smaller than that. So we're going to subtract 9 degrees. Okay, so now we have two equations and two unknowns, so we should be able to solve this for each of these angles. Let's double check. All right, so it's up to you how you want to do it. There's definitely a few different strategies we can use here. I'm trying to see if there's one in particular that seems really nice. I don't think one is all that much nicer than the other, but let's see. We'll start with these two. I think what I would do is maybe solve this first equation for M1, or sorry, for M2, and then plug it into the second equation. So let's go ahead and let's take the first equation and let's solve for M1. So that means, or sorry, solve for M2. So that means the measure of angle 2 is equal to 180 degrees minus the measure of angle 1. And let's go ahead and plug that into the second equation. So the second equation says the measure of angle 1 is 1/2 times the measure of angle 2, which is 180 minus the measure of angle 1, and then minus another 9 degrees. So this is, if I distribute this 1/2, this is 90 degrees minus 1/2 of the measure of angle 1 minus 9 degrees. And then if I add 1/2 to both sides, I get 3/2 times the measure of angle 1. And 90 minus 9 degrees is 81 degrees. So the measure of angle 1 should be 81 degrees times 2/3. Yeah. And I think that's 54 degrees. Great, so that's the measure of angle 1. And now we can just plug this back into either one of my, or any one of my initial equations and solve for M2. I think this one seems the nicest since it's already solved for in terms of M2. So that means measure of angle 2 is 180 degrees minus 54 degrees, which should be 126 degrees. Great. Okay, so just to finish off, I wanted to point out a couple of examples that you could address for in office hours. Oops, yeah, that seems fine. For participation points, these are all in Part B of Section 12.4. So number 23 states that Kent notices that when parallel lines are cut by a transversal, the measures of the angles of the angles outside the parallel lines and outside the parallel lines and on the same side of the transversal, so for instance 1 and 2, add up to 180 degrees. He wonders if this is always true. How would you respond? So basically, if anytime you have parallel lines, if those angles 1 and 2 are going to add to 180 degrees. Okay, that's one question. Also, numbers 26 and 27 would be good to look at. Trisha is finding out how many rays are determined by 3 collinear points R, S, and T, and she thinks there are 6. So she wants to know if you agree. So let's say, so basically she's looking at 3 collinear points R, S, and T, and she says that there are 6 different rays here. So for instance, R to S, S to T, R to T, and so on. And she wants to know if she is correct, basically. Rodney says if a triangle can be acute and isosceles at the same time, and another triangle can be equilateral and isosceles at the same time, then every triangle can be described by 2 of the triangle words. So there must be some triangle that is scalene and isosceles, and another that is right and obtuse. What are the limits of Rodney's conjecture, and what combinations are possible, which are not? I really like this question. I think this would be a helpful question to go through as far as thinking about what things are possible, combinations, is a helpful exercise to do to prepare for the test in this section. So I like that one a lot. Okay, well, I will see you next time.